Hi, my name is Shreyas Sarana, and I will be talking about what Romulus is, the history, the NAE MRE families, and the security of Romulus.
Hi, my name is Darian, and I'll be talking about block ciphers and tweakable block ciphers.
Okay, my name is Elvis Tang. I'm going to be talking about the skinny structure, the tweakable block cipher that the Romulus uses.
So what is Romulus? So a little bit of history about Romulus is an authenticated encryption with associated data. So it was proposed back in 2016, and it's a candidate and still is a candidate of the NIST Lightweight Cryptography Project. So, Romulus consists of a nonce-respecting variant called Romulus N and a misusing resistant variant called Romulus M. Each variant further consists of several parameters having different efficiencies and security characteristics. Romulus is based on Skinny, which is a tweakable blocker proposed at Crypto 2016. Romulus directly uses Skinny as a tweakable block cipher, and the security proof based on the standard pseudo-randomness assumptions of the tweakable block cipher. So a little more history about Romulus is it is a lightweight crypto that refers to encryptions that can be implemented compactly. And it does incorporate both NAE and MRAE. And then go on. The NAE and the MRAE families. So Romulus and Remulus have two families. This is similar to Remulus in a few ways. The N family represented the non-spaced AE, which is secure against non-ducking. The M family represents the misuse-resistant AE. And then moving on to the security of Romulus. So this figure shows Romulus N. So it's the non-spaced AE mode with a stop and middle process and even an or odd AD, with the last process AD representing the encryption process, which is down at the bottom. And then moving on, we have Romulus M. So Romulus M is the misuse resistant AE model with the top process of the AD representing all the cases in between an even and odd combination, with the bottom block representing the encryption. So again, the encryptions are at the bottom.
So I'll be going over block ciphers, and essentially what block ciphers are is that block ciphers are the fundamentals of a tweakable block cipher, and a tweakable block cipher is what Romulus is built off of. So a block cipher, what is it exactly? So it's an algorithm that consists of two inputs, a key K and a message M, and produces a single output, a ciphertext. So, but one of the main issues that a block cipher had was that block ciphers are pseudo-random, so they are inherently deterministic, where every encryption of a given key will be the same, and due to this pseudo-randomness, its security measures are not. So one way where they upgraded to the tweakable block cipher, it allowed for the algorithm to stay secure, but also caused a lot of variability for its users. Tweakable block ciphers consist of 3 inputs instead of 2, which are the keys, message, a tweak, and an output, which is the ciphertext. Under a TBC, under a tweakable block cipher, the tweak and the key controls the encryption M, where the tweak can be easily changed and is much more cost efficient than changing the key. In a tweakable block cipher, the security role is to provide the adversary uncertainty, and the tweak provides variability. And B represents your standard tweakable block cipher, and figure C represents a tweakable block cipher where the key is inside the encryption, so you need to tweak first. Moving on to the next slide. This is just a regular oh, not that slide, but okay. So this is the tweakable chain hash, where a tweak chain initializes with a fixed vector called T naught with another fixed key. After the first encryption is accessed, the message is then padded with ones and zeros until it's the same length of n. N representing the number of bits that message is, and H is going to be the output of the hash. And it keeps doing this until it reaches, until it's no more, or until the hash is produced. Next slide. So tweakable authenticated encryptions, or TAE. So this has the highest security model, since given an O oracle where if O equals to E to K, then the adversary with a tweakable authenticated encryption model with a probability that's less than 2 to the power of negative tau. If O is equal to negative pi, we are providing a random oracle with a non-elegant at most, or non-negligent at most, or exactly at 2 negative tau. So if it is more than 2 negative tau, it won't be able. I won't be. Actually, no, never mind. If A produces an old nonce, it'll be considered incorrect since the nonces will be repeating.
Okay, so I'm gonna be talking about the basic skinny structure that the Romulus uses. So as a skinny structure is a lightweight block cipher, which is going to be either 64 or 128 bit blocks. And the internal state is viewed as a 4x4 square array of cells, where each cell is either a nibble if it's n equals 64, or a byte if it's n equals 128. Then this is also going to be called a tweakable block cipher. Then Tweaky, it follows a Tweaky framework and thus takes away the Tweaky input instead of a key or a pair key/tweak. The user is able to choose what part of the Tweaky input will be the key material. And it's also has 3 main Tweaky sizes, either going to be n, 2n, or 3n. So initialization, the cipher receives a plain text M, then M0K to M1K to M15, where the M are bytes, and the initialization of the cipher's internal state is performed by setting IS to M from 0 to 15. The cipher receives a Tweaky input TK to TK47, where TK are 8-bit cells. The initialization of the cipher's Tweaky state is performed by simply setting it from 0 to 15. We note that the Tweaky states are loaded row-wise. And this is the initial value of the cipher internal state. And the state is row-wise rather than column-wise. This is going to be a more hardware-friendly choice. And this, the skinny runs through something called the round function. Before, the skinny 128.384 originally runs through 56 rounds, but recently they made something called the skinny 128.384 plus, which is reduced to 40 rounds. So it'll be going through 40 rounds of these different transformations. So one encryption round is going to be composed of the following order: subcells, add constants, add round Tweaky, shift rows, and mix columns. So the subcells is going to be an 8-bit S block. S blocks is applied, and it's going to be this is going to be every cell of the cipher internal state, and it's given in hexadecimal notation. Note that the S8 could be described with 8 NOR gates and 8 XOR gates as depicted in this figure, and it takes 8 inputs. So add constants is one of the more complicated functions. So this is stating that it's a 6-bit affine linear feedback shift register whose state is denoted by RC5 to RC0, with RC0 being the least significant bit, and is generated round constants. It's updated as 9, or its function is 9, defined as this. The 6 bits are then initialized to 0 and updated before use in every round. So the bits from the linear feed shift register are arranged into a 4x4 array, and only the first column is affected by the linear feedback shift register bits. And depending on the size of the internal state, the round constants are combined with the state respected array positioning using bitwise exclusive OR. The values of these constants are given here. So this is a add round tweaky, another complicated function. So the first and the second rows of all tweaky arrays are extracted and bitwise exclusive OR to the cipher internal state respecting the array positioning. The linear feedback shift registers used in Skinny to generate the round constants are given here. So shift row, this is a pretty simple one. So in this layer, the rows of the cipher cell array are rotated, but they are to the right. In other words, a permutation P is applied on the cell positioning of the cipher's internal state cell array for all 0 through 5, shown here. So that's pretty much saying that the second, third, and fourth cell rows are rotated by 1 through 3 positionings to the right, respectively. So mixed columns, the last function is going to be each column of the cipher's internal state array is multiplied by this matrix. And then the final array could be given as this test vector. Like the final value state array provides the cipher text with cells being unpacked in the same way as a packing during initialization. So this would be the key. And this is a plain text and then the cipher text. Okay, thank you.